Part C, we're asked to find the first four non-zero terms and the general term for the Maclaurin series representing the integral of f of x. The integral from 0 to x f of t dt, recall, is really just f of x, is the integral of f of x. And then again, just to remind us what the function f of x is, it's this 1 over 1 plus x cubed given by the Maclaurin series 1 minus x cubed plus x to the 6, etc. And we want the integral of that. And so the integral of the first term is going to be x. For the second term is going to be x to the 4 over 4, and that term is minus. Then x to the 7th over 7, and that's positive. That's the first three non-zero terms. And the general term would be negative 1 to the n, and then x to the 3n plus 1, and divided by 3n plus 1. And note that when I write it in this way, I can use the equal sign here because I've represented this by an infinite series. I not only had the first three terms plus the general term, but even after the general term I have plus dot dot dot, and it continues to infinity. So this is the answer for C. Once again, we should be able to get the first term of x, and in this case, when n is equal to 0, x to the 3n plus 1 will just be x. And so that will give us all the values and all the signs that we're looking for here. So once again, how did we find that and how did we know where to start from? I would suggest that you use the general term that you're given and find the derivative or the integral as is necessary, and then start back and look at what we need to start n with in order to get the first term correct. And so that is our answer for part C. So now we're going to use the first three non-zero terms to approximate the integral from 0 to 1/2, and all we really want to do is plug in 1/2 there for x. Just be careful at this point because we're only using three terms that we are actually estimating that integral. And so we substitute x equals 1/2 and simplify. So that would give us 1/2 minus 1/64 plus 1 over 896. Now once again, you don't have a calculator on this particular problem. I would again be tempted to leave the answer just as it is right there. But a little bit of work would give you 448 over 896 minus 14 over 896 plus 1 over 896. And I believe that would give us 435 over 896. Alright, now the next thing that we have to do is to state the properties of the terms of the series that guarantee that this approximation is within 1/10,000th of the actual value of the integral. And this is an alternating series, and so we just have to establish an alternating series converges when the following three things are met. One, that it strictly alternates, and we see that that negative 1 to the nth will guarantee that. Second, that the n plus first term is less than the nth term, which means the terms are getting smaller. And we can see from the three terms that we calculated, 1/2, 1/64, 896, that that is true. And the third is that the limit at the nth term, as the nth term approaches infinity, is 0, and we can see that as well. So as long as those three criteria are met, the series converges and the error will be less than, the magnitude of the error will be less than the magnitude of the first unused term. So when those criteria are met, the series converges. We have to find its interval of convergence, but the magnitude of the error will be less than the magnitude of the first unused term. We're given the interval of convergence of negative 1 to 1 above, and because 1/2 is within that, we know that it converges at 1/2. The error will be less than the first unused term, which is x to the 9th over 9. And when x is equal to 1/2, it would be x to the 10th over 10, which gives 1 over 10240, which is less than 1/10,000th. And we're done.